This morning is p-adic analysis came in history sort of at the end. You know, before there were Sobolev spaces and the Laplacian and so on, people tinkered with numbers and functions forever. I don't think it happened in p-adic analysis the same way. It started right at the top. So I feel that there should be a critical mass of p-adic crunchers and number crunchers and engineers, ideally. So this is somewhat, sorry?
We had dwarf.
Right, but that is already a higher level thing. I was thinking of really sort of
he was
basic.
an engineer.
He was an engineer, that's true. So this is sort of the spirit of this talk. It started with something that Sergey showed to me in 1995. This is solving a monthly problem due to Shalit, I believe. I'm not sure I get the right number there.
Two L's and one. I think it's one T.
One T?
I'm thinking of the right person.
And so it's an elementary thing. He, I think, discovered this by playing around, and I don't know the context. So V3 is the evaluation of 3. He discovered that this always holds. And I think he posed it as a problem, and Sergey solved it by considering the ratio of the two quantities. And showing that there is a continuous p-adic function that interpolates these values. And in fact, the values are actually land in -1 plus dz3. So the ratio is always a unit, and that explains this identity between the evaluations. And he did a few other things that I will get to. For the longest time, since 1995, every couple of years, I look at this and I say, why 3? I mean, it's hard to imagine that there's any result will be valid for p equals to 3 in this way and not for other p's. I mean, what's the story for other p's? So eventually I found a way to think of this for general p. And it goes like this. Let me define the numbers h n of t. T for the moment is just a variable to be essentially the ratio that we have over there, and except that we're going to stick in a factor here of 4 plus t to the n minus 1 minus k. So if t is equal to -3, then we get the left-hand side divided by just the binomial 2n choose n without the n squared. So we'll get to the point to describe where the n squared comes from, which is in itself an interesting thing. So the first thing I want to do is show that these numbers for a fixed t can be interpolated p-adically for the right choice of t. And so this boils down to an identity, which is not hard to prove, and I give what is probably the most complicated possible proof. But somewhat explaining where it came, how I discovered it. So there's a little switch here from the 4 plus t variable to the t variable. And the two expressions are in the sky some sort of hypergeometric thing. And so this is a reflection of basically the monodromy of hypergeometric functions that allows you, so it connects what the function is at 0 with respect to the, well, if you normalize it right, the next singularity in the differential equation, and they have a common area. So this is an expansion, so to speak, at one point, and this is at the other. At least this is sort of a reflection of that fact, but you can give a, or somebody else can give an elementary proof. Okay, but the beauty of this, you see, this looks like essentially the same kind of expression, but there's a beauty here, which is that the variable n appears only in this combinatorial number, so I can easily just erase this n and think of an infinite sum. And so I can consider this expression where it replaces n by a variable x. And now I have a function which, evaluated at x equals to n, gives me the original numbers. And if I take t to be in the right disk, this will converge p-adically. So let me just say that for the moment it would be enough to take a p-adic integer with absolute value less than 1. The combinatorial 2k choose k has a valuation of p that grows at most logarithmically with k. So if we choose t, this guy will win over, and this gives a convergent Mallory expansion of a continuous function, which interpolates these values. So that's the first step. And if p is equal to 3, again, so if we take p to be 3, t to be minus 3, t plus 4 is 1, then this recovers almost what's in here, except for that n squared. But we could do this a little better. So this is a continuous function on CP, but in fact it is an analytic function of x. So to dwell into this a little more carefully, we need to do a little more carefully the study of the evaluations of these coefficients 2k over k here, which are dividing. So if we expand as a formal power series, it's always a, well, you can always do that with any Mallory expansion and see what you get. So let me do that and just for the moment call the coefficients Bn of t. So we can write expression for this. B0 is 0. The function here, if you notice, starts with k equals to 1. So all the binomials are divisible by x. So the function has a value of 0 and 0. And then the rest of the coefficients can be written like this. So there's going to be a lot of formulas here. And that simply comes from writing the binomial coefficient explicitly as a polynomial in x. So these c and k's are integers. And so if we study the expression for this Bn of t, I want to show something about their p-adic valuation so that I can say something eventually about this power series expansion from x. So I pick t, let me call r the p-adic evaluation of t, and now I think of t some element in CP, so r is some rational number. So if r is bigger than p minus 1 over p minus 1, I claim that that the series for Bn converges, and in fact Bn goes to 0 as n goes to infinity. So if the evaluation of t is sufficiently large, then I get a series in t, a convergent series in t, and moreover the terms in this power series expansion go to 0, so I get an analytic function of x in the closed unit disk. So for this, we have to look at the evaluation of k factorial 2k choose k. Well, I don't know how much of this I really want to, let me write it out, but this is the nitty-gritty of this argument. It's just a careful analysis of the evaluation. This here is just the log in base p, a real number. So what we see is that the evaluation of this quantity here has evaluation p of this bigger than r1 minus p minus 1 times k minus log p of k minus r. So if r is bigger than 1 over p minus 1, the k will win over and will give us something that has evaluation going to infinity and shows the series converges. And because the terms start Bn, the series starts with the k's at least n, and each one of them has evaluation that grows, and so that shows that the Bn's go to 0.
This formula here, log p of k plus, is that n over p minus 1?
Yeah, I keep messing up the indices.
Yeah.
Sorry.
That's actually
Okay. Let's see, but we can be a little even more careful
really
than
easy.
this, because we wanted to be able to say something about the evaluation of these two quantities. We took the ratio, so we want to make sure that the ratio, well, we're claiming that we can interpolate it with a continuous function, but we want to say what the range of that function is. So more precisely, if you look at the maximum for k bigger or equal to 1 of the 2k factorial over k factorial divided by k minus 1, this whole thing is 2 over p minus 1, which occurs for k equals p plus 1 over 2. So if r is a little bigger than what this required for the convergence, then we in fact get that the coefficients Bn are integers, and therefore this power series takes the closed unit disk to the closed unit disk.
And for this max, you want a v sub p somewhere?
I do, yes. That's what I do. Over there. Thanks. Okay, so this, now we have a power series that converges in the closed unit disk, is sends the disk to itself. So in particular, the values at the integers are going to be integral, and that gives us the first form of a generalization of that problem in the monthly, which is that we take the theorem is a bit too big for this. We take a u and cp such that the evaluation of u minus 4 is at least 2 over p minus 1. then we get that the size of k equal to 0 n minus 1, 2k choose k, n minus 1 minus k is less or equal to the evaluation, the size of n to n. So notice I stuck in an n here because the function h that I raise as power series starts off with a b0 that is 0. So the whole function can be divisible. You can divide by x, and it still be an analytic function that takes this to the disk. So, so this is the first version of what I think is the general case of that statement that I started with. So just as an example, if we take u to be 1, here I'm going to use u is t plus 4. So if u is 1, t is minus 3, and p is 3, this is the saggy case, where it's a little weaker. If u is minus 1, t is minus 5, and p is 5, then we get something else. So we get, notice that evaluation 5 of minus 5 is 1, which is bigger or equal than 1 over p minus 1, phi minus 1, 2 phi minus 1, which is a half. So we use in the hypotheses. And so we get that the alternated sum of these binomial, central binomials has evaluation, has size, p-adic, 5-adic size, bounded by the size on the right-hand side. Now, so the question I wanted to answer from here is, well, why is it that in the case of p equals to 3, and there's choices, does the result hold with an n squared instead of an n? So the question is, when does x squared divide h in the sense of power series? So that is to say, when is b1 of t, that's the first coefficient, the coefficient of x, equals 0. So, I mean, this is not a completely trivial fact. You have to actually do something. Even in the case of Sagie, you have to prove that a certain p-adic number is 0. And as we'll discuss a few other cases of this coefficient Bn, you can verify to your heart's content that the number is p-adically very close to 0, but unless you know something else, you're not going to be able to prove it's 0. I don't have to tell this, emphasize this too much to this crowd, but so there is a content on the fact that for p equals 3 and t equals to minus 3, this series actually is 0. So how does that come about? So I'm going to change the variables slightly, the sort of more convenient way. And let me write t to be w minus 1 over w squared. And therefore u, which is t plus 4, becomes w plus 1 over w squared. It's a more symmetrical form. And so, for example, if w is the cubic root of unity, a primitive cubic root of unity, then this corresponds precisely to t equals to minus 3 and u equals to 1, which is the original case. Now, you can work with the series that I had for the general Bn. B1 is the ratio of h over x when x is equal to 0, just the linear term in the expansion. And you can work out this as a power series in t to be this. And if you familiar with the proof of a priori of rationality of zeta of 3, you may recall that there are some strange expressions for zeta of 3 which have a form somewhat like this. And that's anticipating a bit of the final thing I will be saying later, the connection with the multi-polylogs, which is the title of the talk. So we need to show that theoretically this power series for t equals to -3 vanishes. Okay, and well, how do we do that? I don't know how to do it just like that, but it follows from a following fact that now here I'm going to introduce one more variable even, called z. So my w is this one here, and I want really something that is congruent to 1 modulo uniformizer, so I want to do this generically. See, the trouble is that I don't know how to prove the identity I want to prove p-adically without going through the complex numbers. So I'm going to prove an identity of the complex numbers as power series, and then I'm going to plug in p-adic numbers into it. So this statement here is a pure power series statement. So I want my power series, my w parameter, to be congruent to 1 modulo uniformizer. So z here is the form or variable that I want to emphasize. And so what you prove is that the power series for v1 of t, but t written in this, in terms of the polarity of w, has this expression. So for w minus 1 to the square equal to t, that's exactly the v1 of t. And I claim that the answer is log w squared divided by this factor. And the proof of this is
you have log of w squared?
w squared.
Oh, so you can bring the 2 out?
You could,
Okay.
but I don't want to.
Except for
P is not going to be 2. So P is not going to be bigger than 2 from. I don't know what time I needed that, but I certainly will. I need it somewhere. So now, how do we prove this? Well, this is as I said, you go through the crutch of the complex numbers, so to speak. And one way to do it is to start with this identity, which my understanding is that this was due to Euler. I mean, that's always a safe thing to say. But I think it's accurate. That, again, something that you can find in Aperi's paper, or at least some of the discussions later. Well, I don't think it's a difficult thing, but I'll want to attempt to prove it. And you can see how this roughly looks like what I'm trying to say if you set x to be sine of theta and w is e to the I theta. Right, so the x is sine theta and w is e to the I theta. Then you're going to get here w minus w inverse, and here the arc sine will become the log. But now you see, now we can look at this as a pure power series expression with rational entries. Now we can think of it p-adically. And if we take w minus w inverse sufficiently small, p-adically, the right-hand side will converge, and it will converge to the left-hand side. Now you'll see this is both great and annoying, because I wish I could do this for the cases that I can't. But, well, to be happy it works here. So, in particular, if w is equal to a primitive root of p root of unity, then the right-hand side equals 0. Because the left-hand side is log of a p root of unity to 0. So that's how you can prove that this number is 0. Because it's the log of a p-adic p root unity. And that's a proof. No, we don't do any approximation. So it's somehow in the spirit of this whole period and L functions business that you prove identities somehow because they come about in some sort of meaningful way. All right, so that shows that now we can specialize that statement that I made a little more precisely. So as a corollary of this is that we take zeta p in Cp to be a primitive p root of unity. Then V1 of zeta p minus zeta p inverse squared is equal to 0. So this thing is what I was calling T, and notice that the evaluation of P of T is precisely equal to 2 or P minus 1, so we are in the range where things converge, and we conclude finally the closest analogy or generalization of the original problem in the monthly is that this zeta p plus zeta p inverse to the 2n minus 1 minus k is less or equal to n squared 2nn. So the vanishing of this coefficient gains us a power of x, and that's what we see this n squared. And so this for p equals to 3 is almost the original question, except that the original question had an equality. So you can ask yourself, when does an equality hold there? And let me just make a small comment that you can verify that with these choices, the coefficients in the power series of x are integers and are divisible by p if n is bigger than p minus plus 1 over 2. If you recall, I stated something about the maximum of those valuations and when it occurred. So once you pass that maximum, the coefficients are actually p-adic are divisible by p, which means that h of x with our choice of t is divisible by x squared. We know that, and is in fact congruent to some polynomial. AP is a polynomial of degree at most p minus 3 over 2. So if AP of x has a root mod p, then this ratio is divisible by p, and so there will be a strict inequality here for any n congruent to that root. And if the polynomial doesn't have any root in mod p, then this ratio is a unit for all those n congruents to that n 0. So that means that this inequality will hold, will have a strict equality for some congruous classes mod p and some equality for others. And you know, the feeling I can't help myself, I just plotted a few of these. So for p equals to 3, the polynomial is a constant. So for all n's, we have exact equality, which is what Sagi proved. And then, for example, for 5, we have x plus 2. So that means that as long as x is not minus 2 mod 5, we have equality. Otherwise, we have strict inequality, and so on. And so basically, these polynomials often, but not always, have a root mod p. So this phenomenon, so this is no roots mod p, this is a root mod p3, and this has no roots, and so on. And so, for example, for p equals to 61, it has 3 roots mod p. I don't know what that means. Okay, so now let me get into the stuff of the title. And the reason I chose to give a talk about this is because there's some stuff that I can't yet prove, and I would be very happy to discuss it with whoever knows more about what's needed than me. So when Don proved that B1 was 0, so you get this n squared in the statement, and then he looked at the further coefficients, and playing around with congruences, Sagi noticed that apparently B3 was 0. That is to say, computed for many n's and studied the congruences and between the two sides of the original question, and the congruences behaved in a way that was equivalent to saying that this third coefficient was equal to 0, and he asked the question, what is B2, which is not 0? In the sense of, is this number B2, which is now a p-adic integer, does it have any kind of closed form? And well, it won't be a surprise. It seems to me that Don's intuition was right on, because what I claim, and this I claim meaning that I'm sure it's true, but I'm an epsilon away from the proof, is that B2 and B3 are p-adic zeta values. And so B3 is 0 because it's a value of the 0 function. So to prove that B3 is 0, again, you can compute to your heart's content, and it will be as 0 as you like. But to actually show that it's 0, you need something. And if you can connect it to the value of a p-adic zeta function that happens to be the identical 0 function, then you have a proof. And that's exactly what I think the proof should go, how the proof should go. So morally, B3 equals an expression which is an expression giving you a p-adic zeta function. And if you're familiar with p-adic zeta functions, because of the functional equation, if you happen to hit the wrong parity, the things you're trying to interpolate are 0, and so you just get the 0 function. And that's what happens in the case of B3. And in the case of B2, it's just a p-adic zeta function, which is not 0. But so that seemed to me. So let me explain where the this sort of just didn't come out of nowhere. I mean, it sort of dawned on me slowly that this had to be true. And as I said, I'm sort of an epsilon away from proving it. So let's try again to play the same trick of going over the complex numbers, hopefully writing power series expressions that then we can plug in and think of them p-adically. So let me work over C and try to express these bn's in a different form. Okay, so by a simple manipulation, you can rewrite the original expression I had for H as follows. And then this is following an idea that Don uses to prove that B1 is 0. You can write this ratio of k squared factorial over 2k plus 1 factorial as a beta integral. And now you have a sum of a geometric series inside the integral. So you can write this whole function as the integral from 0 to 1 of 1 plus t z, 1 minus z, to the x minus 1 dt. So the bn's are the power series coefficients of this as a function of x. So if you differentiate with respect to x, you're going to get logarithms. And so you get the bn of t is log n minus 1, 1 plus t, z, 1 minus z. Okay? So that starts to look interesting for some people. And now you try your best. And you can try a substitution. And let me try this. And you get that the expression, I'm not sure if I should write everything down. Maybe I will. I'm just changing variables so that my quadratic factor in here becomes a simple factor 1 minus u squared. Here gamma plus and gamma minus are to the limits of the integration when you change variables. And gamma plus, gamma minus, 1 plus minus gamma, and gamma is, now you probably know what I meant by tinkering and number crunching and engineers. So now this integral, you can break this integrand as 3 terms, 1 plus 4 plus t, which is what I called u before, times 1/2 of 1 minus u, and 1/2 1 plus u. Write the log as a sum, collect all the terms, and what you're going to get is a massive or a complicated thing that involves integrals of this form. The main terms are of the form log to the k of 1 minus v, and make one other small change of variables. And the key terms in this expression have this form. So if you played around with polylogarithms and multi-polylogarithms, you may have encountered things like this. People call them the Nielsen polylogs. For small values of n, these integrals can be computed in terms of the usual polylogs. For higher values of n, or rather for arbitrary pairs of k and the other exponent, these are not expected to be reducible to usual one-variable polylogs. But for n equals to 2 and 3, they reduce, everything reduces to single polylogs. And let me give you the expression for n equals to 2. So for n equals to 2, still this is all happening in the complex numbers. So if t is less than 1, b2 of t, we can write it like this. Like 2 is the usual dilogarithm. Okay, so now if we make a leap of faith, and then here's where the epsilon is, because I don't know how to argue that this should hold p-adically. So if this holds p-adically, then I can plug in, for example, I'm going to concentrate only in the case p equals to 3. So I plug in t equals to minus 3, and let me keep, so if t is equal to minus 3, let's work out what this is. Well, gamma is equal to square root of minus 3, and gamma plus minus is equal to a cubic root of unity, a primitive cubic root of unity. So if I plug it into this here, again the log terms go away, because we have log of a primitive cubic root of unity p-adically. So these terms are gone, and here we get lie 2 of a p-adic, a third cubic root of unity minus lie of the cubic root cubic root inverse. So this, if of the complex numbers, equals a zeta value, or rather an L function. And Coleman proved that that statement actually holds p-adically. So Coleman proved that, like, well, something which in particular implies this, and I think I have to divide by -3, but just the rough shape of this, it's the p-adic zeta function, and I think it's evaluated at 2. I'll just leave it at, I forget exact form, but it has to be 2. Because, so it's a p-adic version of an identity between special values of L functions and dilogarithms in this case. So once we make that leap of faith that this identity should hold theoretically, then this is what we expect. We expect that, so this is a proof, so to speak, or an indication that B2 of -3 should be this p-adic zeta function at s equals 2. And a similar thing happens when you consider the case of n equals to 3. Now you get an even more horrible expression involving the trilogarithm. And again, by the results of Coleman, you get a value of a p-adic zeta function, but it's the case of a p-adic zeta function which is identically 0 because of the parity reasons. So the thing I would like to discuss with anybody who's interested is exactly how to go from this. Maybe this is not quite the way to go, but an attempt would be to try to understand this p-adically, and it's basically a question of analytic continuation. Because we're trying to evaluate, this is centered around 1, and this is centered around 0. So we somehow have to argue that, that the statement still holds as you move to another disk. Okay, so let me finish with one last thing, which is another identity for this Vn, which involves multi-polylogarithms. So those Nielsen polylogarithms that appear in my proof, in the proof so far, I mean, I just didn't want to deal with them, so I tinkered in some more. I found a different format, and this is so an alternative method to study these coefficients. And this is basically the method that Sagi used. Is to do this. I mean, let me define little h, just for convenience, to be the original h divided by x, which was divisible by x anyway. So then you check that the numbers h of n, which were the original motivation, satisfy a recurrence. And you can think of little h as a power series in T, whose coefficients are polynomials in x. So this identity holds for x equals any integer, any positive integer n, and so it has to hold for all x. So if you set n to be, this is 2n plus 1 of this. If you set n to be -1/2, then the left-hand side vanishes, and you can compute h of -1/2. Deduce it from here. And if you, so this gives us that h of -1/2t is equal to 2 over t plus 4. And now by induction, you have the original term in the recurrence. So by induction, you can prove that h minus n plus 1/2 of t is 4, t plus 4, n 2 inches n. K, which is k, 16t plus 4, n minus 1 minus k. So this is another manifestation of sort of monodromy, because now what we did is some kind of transformation in the t variable, taking t to 16 over t plus 4, and relating the original series of t with a somewhat similar series or sum at this new parameter. So since this is valid for any n, we can deduce from here that, in fact, h of x satisfies a functional equation like this, which is modular looking. You change both parameters by a linear fractional transformation, and you get a relation with the original function. Now notice that the miracle that occurred is that you may recall that the original little h had a 2k choose k in the denominator. And now this flipping of the variables put the 2k choose k on the numerator. Okay, so there's some sort of flipping of everything around. And well, this is a bit of a manipulation. Not too hard. None of what I've said is hard. It's just a question of patience. You see that you can write this as follows. Product j equals 0 to k minus 1. 1 plus x over j plus a half. Just basically taking this and writing it out. And so if we want the Taylor coefficients of this, see, the beauty of this is that this is the original series, which equals this one. This one is a lot easier to deal with. And so we can get the coefficients in the power series expansion on the left by looking at the right. And that gives an expression like this. And this is a multi-polylog. Or it's a linear combination of multi-polylog values. So this is a separate expression for the same coefficient. And if you look at n equals to 1, it reduces to the original thing that I mentioned with the arc sign. And for n equals 2 and 3, it will give identities between this and the usual dilogarithm and the usual trilogarithm. But for higher values of n, I have no idea how this expression can be manipulated. And so what this shows at least is that the coefficients then in the power series expansion of this function x can be given in terms of polylogs, for what it's worth. Now, once the n equals to 2 and equals 3 case seem to give say p-adics zeta values, it seems natural to look at the higher ones. And this is where is a question that I pointed out in the email to the group, is that it would be nice to have a good Lindep p-adic, because one can start playing games between various constants the same way that I'm used to playing games in the complex numbers. And so in that spirit, I computed the values of B4 and B5 at the original choices, p-adically, and they seem to be related to zeta 3. Okay, in the sense that you compute both sides and they agree as long as with the precision that you work with. And so, but this I have no reason a priori to expect this to happen, because the two expressions I have for them are complicated things, either these Nielsen polylogs or these multi-polylogs. And I suppose there must be conjectures that relate multi-polylogs to zeta values, which I don't know all the details of that. It might be a conceptual way to understand why this should happen, but that means that I've much farther removed from a proof than the case 2 and 3. And for larger values of n, then this appears to be no relation, but again, if one could have a supply of constants or and a good Lin-Deb algorithm, one could play some games with it. And so, to me anyway, what this suggests is that there could be a number of interesting numerical things that one could do in this setting of periods and special values of L functions, but on a three-adic or a p-adic setting. So I'll stop there. Thanks. Question?
So for the higher numbers, are you conjecturing that you'll be able to find any polylogs, or do you expect that it's just going to be some higher
Well, so what I can only claim is that numerically these higher constants seem to be related to three-adic zeta values.
Yeah.
And a possible proof of that would be to use this expression and somehow manipulate it into single polylogs, and then use Coleman's result. But that just may be the wrong approach. I just don't know. All I'm saying is that I even thought of the relation with three-adic zeta functions only through the polylog story that I could see was valid for n equals 2 and 3. But even that may not be the right way to prove it, or the way to prove it. Maybe a direct way, which I don't know.